Hi everyone, welcome back to BSc Chemistry Study Room. If you are new to this room, please subscribe for more video updates. And if you have already subscribed, please click on the notification button for more video updates. So today we are going to discuss under hydrogen spectrum. The Nelbo's atomic model provides explanation on the atomic spectrum of hydrogen reported by Johann Balmer. Johann Balmer was the first scientist who reported hydrogen spectrum. So this is how the structure of Nelbo's atomic model looks like. Johann Balmer says every electron moving from any initial point, the destination of that electron will be where energy level is equal to 2. This is electron moving from n is equal to 3 to n is equal to 2, n4 to where n is 2, and n5 to where n is equal to 2. From anywhere, let's say infinity, electron moving from any point as the initial point will stay where n is equal to 2, reported by Johann Balmer, who says every electron moving from any point, the destination will be where energy level is equal to 2. Johann Balmer reported. Not all gaseous elements emit spectrum in form of series of lines, hence these lines are called line spectrum. Here shows the different series for hydrogen reported by different scientists, which this series must always be remembered in order to solve numerical problem whenever given. This is the N final. N final shows the last destination of each electron coming from any point, any initial point, let's say infinity. This is the Lyman series. The Lyman series shows that any electron moving from any initial point, let's say it is coming from infinity or to other points, so the last destination of that electron in Lyman series is the energy level where n is equal to 1. This N final shows that the last destination of each electron coming from any initial point in Lyman series is where NF is equal to 1, the destination of that electron. So let's see the Balmer series. Balmer series shows that any electron moving from any initial point, let's say from infinity, the destination of that electron will be at the energy level where N final is equal to 2. For Balmer series, N final is equal to 2. And let's see the Paschen series. Paschen series is the series whereby each electron coming from any point, its final destination is where NF is equal to 3. For Paschen series is electron moving its state at NF is equal to 3. Let's see the bracket series. Bracket series shows the destination of each electron as the energy level where NF is equal to 4. For each electron moving from any initial point, the energy level is 4, the destination. Pre-pand, the destination is equal to 5. Each electron moving from any point, let's say infinity, the destination in P-fund series is where energy level is equal to 5. This is continuum. This continuum shows no limitation. This shows that each electron may come from anywhere. The initial point may start from anywhere, let's say infinity. Here shows the corresponding series for each series. Number 1, Lyman series correspond to where NF is equal to 1. That is the destination final is equal to 1. And Ni may start from any point where n is equal to 2, 3, 4, 5, 6 to infinity. And number 2, Balmer series correspond to where NF is equal to 2. And n initial may start from 3, 4, 5, 6 up to infinity. And number 3, Paschen series correspond to where NF is equal to 3. And n initial may start from 4, 5 up to infinity. For brackets correspond to where NF is equal to 4, and Ni, that is n initial, may start from 5, 6 to infinity. For phi-pand, NF correspond to 5 and Ni may start from 6, 7 up to infinity. So this N final shows the last destination of each electron coming from any initial point, while the Ni's shows the starting point of each electron. So this in general equation was found to be valid for all the line in the hydrogen spectrum called Redback equation. This equation satisfied any calculation in hydrogen spectrum, and this equation is called Redback equation. And this Redback equation is given as 1 over wavelength is equal to RH into 1 all over NF square minus 1 all over Ni square, where this NF square shows the destination of each electron coming from anywhere, and Ni shows the starting point of each electron, where this equation is given as wavelength is lambda. Given wavelength R is a Redback constant, and it is given as 1.09678 times 10 to the power of 7 per meter, and N final shows the final energy level of lower energy. That means the N final. So Ni is initial energy level of higher energy, the starting point of each. So let's see some calculation. Number one says calculate the value of the wavelength in Balmer series. Don't forget it is said in Balmer series. When Ni is equal to 5 and take RH is equal to this value. So this value is given is this constant. So by using this Redback equation, which says 1 all over wavelength is equal to RH into 1 all over NF square minus 1 all over Ni square, we substitute the value of RH, which is given. So now we have 1 over wavelength is equal to this value into 1 over 2 square. This 2 square shows the N final, which is said in Balmer series. In Balmer series, N final corresponds to 2. The destination of each electron in Balmer series coming from any point is where N is equal to 2. So that is why we substituted NF as 2. So, and Ni is given as 5. That is why we put pipe. So 1 over wavelength is this value into 2 square is 1 all over 4 minus pipe square is 25. 1 all over wavelength is equal to this value. When we open the bracket, we have 0.21. So by multiplying this value with what we have in the bracket, we obtain 1 over wavelength is equal to 2.303 times 10 to the power of 6 meter per meter. So by cross multiplying, we obtain wavelength. This implies that wavelength is equal to 4.342 times 10 to the power of minus 7 meter. But always leave your answer in nanometer. So since we are going to leave our answer in nanometer, we have to convert meter to meter by taking this decimal point to 2 right. That is, we have 434.2. Then this 7 becomes minus 9. Then we have 434 nanometer. So now let's move to problems number 2. Number 2 says calculate the wavelengths of the first spectral line. First spectral line, don't forget. In Lyman series, in the spectral of atomic hydrogen, take RH as this value will always be given. It is constant. So use a Redback equation which says to obtain wavelength. So 1 over wavelength will be, we substitute the value of RH is given into 1 over NF square is 1. The Lyman series N final correspond to 1, if you can recall. So, and minus 1 all over 2 square. This 2 square shows the first spectral line for Lyman series. Ni, the first spectral line, if you can recall, we said in Lyman series, N final in Lyman series correspond to where NF is equal to 1. And the Ni initial point, the starting point in Lyman series may start from 3 to infinity. So the first spectral line is where Ni is equal to 2. That's why we substitute 2, which gives 2 square. So 1 over wavelength is equal to 1.09678 times 10 to the power of 7 per meter into 1 all over 1 square minus 1 all over 2 square gives 0.75. So multiplying these to these, we have 1 over wavelength is equal to 8.2259 times 10 power 6 per meter. By cross multiplying to obtain wavelength, wavelength is equal to 1.216 times 10 to the power of minus 7 meter. So we need always our answer to be in nanometer. So we convert meter to nanometer by taking this decimal point into 2 right place. So the 7 will be minus 9. Therefore, we obtain wavelength equal to 1 to 1.6 nanometer. Calculate the wavelength of radiation emitted by an electron from infinity in Balmer series. And from infinity. RH is given as this value is always given. Using Redback equation, to obtain wavelengths by substituting this value of RH and 1 over NF square. NF is 2 from Balmer series. The destination is 2 square. So minus 1 all over Ni square. This Ni square shows that the position where the electrons start coming. In the question, it says the electrons start coming from, let's say, it said from infinity to where NF is equal to 2 in Balmer series. It stayed at Balmer series, from infinity to Balmer series. So we substitute Ni as infinity, and then we square the infinity. So 1 all over wavelength will be this value into 1 over 2 square is 1 over 4 minus any infinity square is equal to 0. Infinity square is 0. So we obtain 0, 1 over 0. Then 1 over wavelength will be this value, and this bracket 1 over 4 gives 0.25. So by multiplying the brackets in the outside bracket, we obtain 2.74, 2 times 10 power 6 per meter. By cross multiply to obtain wavelength gives 3.6470 times 10 to the power of minus 7, and we always need our answer in nanometer. So we convert meter to nanometer by taking our point to 2 decimal rights, 1, 2, and this minus 7 will be minus 9. Then we obtain 364.70 nanometer. So that is the answer, 364.70 nanometer. So this is the end of our today's lesson. Don't forget to like, comment and share. And if you have any question, please drop it in the comment section below. And don't forget to subscribe. Thank you very much. Thank you for watching.